as an immediate corollary to the concentration inequality for chi-square distributions. We'll give a concentration inequality for a Gaussian random projection, which I'm gonna write as a lemma number 2. Let x be a vector in Rn, capital N, a positive integer. Let k be a positive integer, and a matrix A that is k by n, whose entries are sampled independently from standard normal distribution. Namely, A is a k by n Gaussian matrix. Then for any epsilon between 0 and 1/2, the probability of the Euclidean norm of 1/k square root times ax Euclidean norm squared lying between 1 minus epsilon times norm of x squared and 1 plus epsilon times norm of x squared will be bounded below by 1 minus 2 times e raised to the power k divided by 4 times epsilon squared minus epsilon cubed, which is really close to the concentration inequality we derived for chi-square distribution. Actually, chi-square distribution is defined through normal distributions, so you can try to prove this by yourself as an exercise. But I will show you the proof anyway. Here, norms are all Euclidean 2 norms, but I will choose to omit those subscripts. Okay, now let's prove this. Suppose the entries of A are denoted A sub ij. Now let x hat denote the product of the matrix and the vector x. And we compute the expectation of x sub I tilde squared, namely the squared ith component of this vector x hat. By the matrix multiplication, you know this is, and we expand this. Here, aij, ail are all sampled from standard normal distribution n01 independently, so they are random. But xj and xl are deterministic, so we can pull out this coefficient. Now, look at random variables xij and xl. They are identical when j is equal to l. When j is not equal to l, they are independent, so we can split this into a product. Observing that the expectation of aij and expectation of ail are both equal to 0, because they are both mean 0 random variables. They are all standard normals. So when j is not equal to L, this guy will become 0. When j is equal to L, it will become expectation of the squared Aij. Hope this makes sense to you. This follows from expectation of Aij equal to 0 and the independence of Aij and AIL when j is not equal to L. Okay, good. But what is expectation of Aij squared? This is equal to 1. Because Aij is a standard normal random variable. And this is precisely just equal to the sum of squares of xj's, which is simply the square of 2 norm of x. So it follows that if you divide both sides of this equation by x norm squared, the expectation of xi hat squared divided by the norm of x squared is equal to 1. And meanwhile, the mean of xi hat divided by x is equal to 0. What does this tell you? This tells you, if you observe that this xi hat divided by the norm of x, noticing that norm of x, this is a constant, this x is deterministic. So this quotient is again a linear combination of standard normal random variables. So and this quotient is a linear combination of independent standard normal random variables. This guy together with this fact tell you that this thing must be again a standard normal random variable. And they're what? I hope you have learned this fact from your first probability class. A linear combination of independent standard normal random variables is again a normal random variable. And because it has the mean 0 and variance equal to 1, so it has to be a standard normal random variable. Okay, now we can finish the proof. So let's recall lemma number 1, which says when Q is a chi-square distribution of k degrees of freedom, then we have this concentrated inequality. We're just going to apply this to this situation. What we do is that we look at ax norm squared divided by x norm squared. This A is a Gaussian matrix of size k by n. With our previous notation, this is x hat. So we just explicitly write this out. X hat will have k components because A has k rows. But what is this? We just proved that each xi hat divided by the norm of x is a standard normal random variable. So this guy is the sum of k squares of standard normal random variables, independent. So this guy is a chi-square distribution with k degrees of freedom. Therefore, the probability if we divide all sides by the norm of x squared, so we can apply this lemma 1 to this situation and get this is bigger or equal to 1 minus twice of e raised to the power negative k times epsilon squared minus epsilon cubed divided by 4. So we are done with the proof of our lemma 2. So if you move this k inside here, you get 1 over square root of k. And you multiply all sides by x norm squared. This is precisely this.